Alright, in this video we're going to continue our discussion on fluid power with hydraulic power. So we talked about pneumatic power and how that was the use of gas flowing to create power. Here we are going to talk about hydraulics, which is the use of liquid flowing under pressure. So pneumatics is the use of gas flowing under pressure. Hydraulics is liquid flowing under pressure. And there's a cool animation to go with that. Okay, so here are some just pictorial examples of hydraulic power. This fire truck would be using some hydraulics to, say, extend this ladder. As you see right here, that's a hydraulic system. And then the same thing here, putting out these supports uses a hydraulic system as well. Okay, so they use relatively incompressible liquid. They have a slower, smoother motion than a pneumatic system. They're more precise. They lubricate naturally, so we don't have to add any kind of lubricant to them. And they generally produce more power. Okay, so if you need more power in your system, tend to want to go with hydraulics over pneumatics. Again, I'm not going to talk about the initial uses. Water wheels is a hydraulic use there, but we're going to move forward here through that. Okay, so a hydrodynamic system, fluid is in motion, force and energy are transmitted by flow. So here's a water turbine. Hydrostatic systems, fluid does not flow quickly or continuously, and the fluid is pressurized. So here is an example of using that in this machinery to help load these logs. Alright, so we talked about Pascal's law in the last video, and that was that pressure is equal to force divided by area. Let's see if this works. If we click an arrow here, you can see that we've got a hydraulic press going here. Okay, moving forward. Alright, liquid flow. So we got flow rate, the volume of fluid that moves through a system in a given period of time is our flow rate. The flow velocity is the distance the fluid travels in a given period of time. So we take the distance divided by the amount of time it takes it to travel that distance. That would give us our flow velocity. Okay, and then here are some units. So flow rate is, we're going to use Q to represent flow rate. That's in gallons per minute. Flow velocity is in feet per second, and then the area is in square inches here. Okay, so flow rate, flow velocity, area. And the formula that involves those is simply that the flow rate is equal to the flow velocity times the area. So here's an example. A flow meter attached to the main line in the hydraulic system measures the flow rate at 15 gallons per minute. The line has an inside diameter of 2 inches. What is the flow velocity in the meter? So our flow rate is 15 gallons per minute. The diameter is 2 inches. We want to know the flow velocity. Because we're dealing with diameter, we've got inches here, we do want to convert the gallons per minute to cubic inches per minute. So that is a conversion that you would probably just want to look up. This would be on your PLTW reference sheet, but 1 gallon is 231 cubic inches. So 15 gallons would be 3465 cubic inches per minute. And just round that up to 3,500. So there's our flow rate in cubic inches per minute. Again, the diameter is 2. Our area, using the diameter, I'd split that in half, so our radius is 1. So our final area is 3.14 square inches. So the flow velocity is simply going to be the flow rate divided by the area, which would give us a flow velocity of 1,100 inches per minute. Here's an example using mechanical advantage. We've got force at the output and force at the input. So we've got an elephant standing here and a mouse standing on this one. Mechanical advantage is simply the output force over the input force. We talked about that at the very beginning of this class. Is one of the first things we talked about was mechanical advantage. A force of 100 pound-feet is applied to the input cylinder of the hydraulic press seen below. What is the pressure in this system? How much force can the output cylinder lift, and what is the mechanical advantage? So here we just want to list all the input data and all the output data. So the input force is 100 pound-feet. The diameter is 4 inches. We're going to find the area input using that diameter, and then the pressure. And then we've got all of our output information. So the area of the first cylinder, the input cylinder, the radius was 2. So we just use pi r squared, and we get a final initial area. This first input cylinder is 13 square inches. The output cylinder has a radius of 6 inches, so we do the same thing there, and we get an area of 110 square inches. And the pressure in the system is simply just force divided by area. So our force is 100 pounds, and the area, the input area here is 12.57 or 13, however you want to use that. So our pressure, input pressure here is 8 psi. Find the force that the output cylinder can lift. So we would take that pressure, which was 8, and set that equal to our F out over our A out. Well, we already found the output area, so what is the output force? And we would simply take the 7.955 and multiply by the 113, which would give us essentially 900 pounds. So now that we have our input force was 100 pounds, our output force was about 900. What is our mechanical advantage? That's simply just going to be our output force divided by our input force, which is going to give us a mechanical advantage of 9. Okay. I'm going to stop there. I think that's going to be enough information to do the worksheet. We can talk about these other concepts at a later date.